Okay guys, in this last video we're going to take a look at a special type of geometric series referred to as the infinite geometric series. And the reason why is just because we're going to be looking at a series where we're not adding together just maybe the first n terms of your sequence or your series, but what if I wanted to add up all infinitely many? Now, one thing is worth mentioning here. We don't ever find infinite sums or infinite series with arithmetic things. Can you imagine, what if I took something that was arithmetic, like was going up by 2's every time, and I said, what happens when I add together the first, say, 5 terms? We actually get something, but what happens when I get a sum of the first infinitely many here? This sum here, this is sum, is infinite. Okay. The thing is, if you add together infinitely many numbers, they're always getting bigger, always getting smaller, say, by the same amount. You're going to get infinity or negative infinity. But when it comes to geometric things, we can actually get a finite or countable sum for an infinite thing. So you might ask yourself, how is this possible? Well, let's consider this geometric sequence right here, 1, 2, 4, 8, 16, and so on and so forth. I can see that this is just my doubling sequence right here. So with respect to being geometric, we can see that there's a common ratio between my terms here. But my common ratio is bigger than 1, which means these terms keep growing bigger and bigger and bigger. So what would this imply if we tried to do an infinite series here? That is to not only add up the first 5 terms, but all infinitely many of them. Again, we would have a sum that is infinite. Okay, and the reason why is because each successive term value is growing larger and larger, and that's due to the fact that our r value is bigger than 1 here. What if, though, we were to take a sequence that maybe has something like this: 16 plus 8 plus 4 plus 2 plus 1 plus a half plus a fourth, and so on and so forth, plus an eighth. We've got something where our r value in this case would be times a half. Okay, so less than 1. If you're talking in exponential lingo, we would say that this would be an example of exponential decay over time. But you're always adding on something that's continuously getting smaller and smaller, closer and closer to 0. So you can see that if I were to continuously get smaller there, the fact that I'm asking you to add up infinitely many numbers that are continuously getting smaller actually leads us to what we call a finite sum, a countable sum. So this right here will have a finite sum. And the reason why, we're going to say because r is less than 1. Or as a matter of fact, I'm going to say r is between 0 and 1. So looking up here, you'll notice instantly the first thing I want you to read here is that we're able to find the finite values for an infinite geometric sum or series if and only if the value of r is a proper fraction. So I'm going to write this here, a proper fraction. You could also look at it as a decimal between 0 and 1, but neither equal to 0 nor 1. But we say the sum of all the terms of an infinite geometric series is given by this. So we say a1 plus a2 plus a3. If we sum all the terms starting at the first term and going on forever and ever of this sequence given by this rule ai, we're going to first of all acknowledge that we just write s. Now you're going to notice that it doesn't say s sub n, it just says s. The reason why we just use s is because this is the sum of all infinitely many terms. Okay, so as we look at these sums, we actually have rules for these as well, and I'm going to share this one with you now. You definitely want to make sure you highlight this here, but it says that the rule for an infinite sum of a geometric sequence is as follows, and that is to say that we're going to cross out this s sub n here. We're just going to write in s. The sum of all of the terms, we'll write it here, is equal to the value of our first term over 1 minus r. So this, I do want to comment, if you were to look at the sum of the first n terms of a geometric thing, it's the first term times 1 minus r to the n over 1 minus r. This is very, very complex. This right here is actually very, very simplified. You'll notice that n doesn't even matter here. There is no n anywhere in this expression on the right. There's no n in the expression on the left. So as we look at these infinite sums here, we're going to write down our needs. This is pretty cool. I only have 2 needs here. The first one's going to be the value of my first term, and the next one's going to be r. I need to know these 2 things. So let's go ahead and take a look at some infinite geometric sums here and see what we can determine. So it says, would the following sums have as values? I'm not sure what I meant to write there. Find the following. Maybe this. Would the following sums have finite values? Maybe, I think. just to ask the question, if I add these up, would I actually get a number, or would it just go to infinity? It says, try making tables to show that n in one column and s sub n in the other here. Well, basically, what I want to do is kind of look at this sum over time. So I'm going to put n here, and I'm going to write s sub n here, where this represents the sum of the first n terms. So you notice if I start at the first term here, at my first term, the sum of the first n terms is 1. As we move to the right, though, at my second term, if I add up the first n terms, the first and the second term added together is 3. If I go to my third term here and I add up the first 3 terms here, then S3, or the sum of the first 3, is 1 plus 2 plus 4, so I get 7. If I add up the first 4 terms here, it'd be 1 plus 2 plus 4, which is 7, plus another 8 is 15. And if I add up the first 5 terms, for instance here, I'd have to add on another 16 there, so 31. You can see that as n is getting bigger and bigger, this sum is growing larger and larger. So one thing that I would argue is, because the r value here, which if you haven't written it down yet, maybe we should do that. Because the r value is bigger than 1, then our terms are always going to be growing bigger and bigger. And because of this, when we try to perform an infinite sum, we're going to have something that grows without bound. And so one thing that we're going to make sure that we write here is this. I'm going to type it this time. This infinite sum has no finite value. This is because r is equals 2, and that is bigger than 1. The terms, therefore, grow in size indefinitely. So this is kind of a wordy, I suppose, way to write this. If at all you told me that, hey, the terms just keep getting bigger and bigger, so like if you add up infinitely many of them, you're going to get infinity, that'd be important to me. It'd also be important that we recognize that this happened because our r value is bigger than 1 here. Now, if you look at this last series here, I suppose we're going to make a table again here for the sum of the first n terms. So this time, again, this isn't a sequence table. This is a table where we put in the n and the sum of the first n terms here. So if I add up my first n terms here, where n is 1, well, the sum of the first term, one term, would be 1. If I add up the first 2 terms, that would be 1 plus a half here. 1 plus a half is 1.5. Okay, so I'm going to write this as a decimal, actually. If I add up the first 3 terms, I get 1 plus a half plus 0.25. This is 1.75. If I were to add up the value of the first 4 terms, I get 1 plus a half plus 0.25 plus 0.125. So you get 1.875. And if I add up the first 5 terms here, I mean, I could grab my calculator here and say, you know, what's 1.875 plus 1 divided by 16, which is our 1/16th here. You'll notice that I get 1.9375. So what I want you to notice is that because each of our terms from term to term is getting smaller, that is to say that our r value is less than 1 or between 0 and 1. Well, then this is going to mean that we're decaying. And because each term is continuously getting smaller, then when I add up infinitely many of them, I actually get a sum, a finite sum here. So what I'd like to do is argue what would happen if we were to continue to add on more and more terms here, the 6th term, the 7th term, the 8th term. What do you feel like this is getting really, really close to? And I would speculate that it's kind of getting really, really close to 2. So here's what we're going to do here. We are going to find the value of the sum of the first infinitely many terms here. And so for letter B, or this second bullet point here, we're going to write S. In this case, we're going to need 2 things here. We need A1, which is 1, and we need R, which in this case is a half. Now I'm going to box these so we can see them here, but we get the value of A1, which is 1, over 1 minus R, which in this case, I'm going to treat the denominator as exact values. I want to use exact values so that I don't get a decimal here. So 2 halves minus 1 half, if we're getting a common denominator down there. 2 halves minus 1 half is 1 half, and our rules for dividing with fractions is we're going to multiply instead by the reciprocal here. So we end up getting 1 times 2. That means that indeed, that if I were to add up all infinitely many of these numbers here in the series, I do, as a matter of fact, get 2 is my infinite sum. So just wanting to know when we can expect to see an infinite sum, it's only going to be if our r value is less than 1. And when you do have an infinite sum, make sure that you're using this rule right here, which is a little bit more succinct than our sum of a finite geometric series. Cheers.